All right, let's jump right in. We're about to unpack one of the biggest, most stubborn paradoxes in all of physics. It all starts with Einstein and his most famous equations. He himself had this nagging feeling that one side of his theory was, well, unsatisfying. Today we're going to see how that feeling turned out to be a massive understatement, leading to a problem so deep it's been called the bone in our throat. So here's our roadmap. We'll start with Einstein's original complaint and watch it blow up into something called the vacuum energy catastrophe. From there, we'll explore a really different, kind of radical new solution, a geometric filter. We'll even use a simple hanger hook analogy to get our heads around how it could literally make the vacuum invisible to gravity, offering a structural fix to this 100-year-old headache.
Wolfgang Pauli, who was one of the absolute sharpest minds in physics, basically laid it all out right here. He said it's just obvious from looking around that the energy of empty space, the vacuum, doesn't create gravity. Why? Because if it did, we literally wouldn't be here to talk about it. The problem is, for almost a century, our best theories have been screaming that it should. This quote, this is the heart of the whole mystery we're diving into.
Okay, so let's start with that complaint from Einstein. The core idea behind general relativity is just beautiful. It says that all forms of energy and momentum tell spacetime how to curve. And in turn, that curvature tells matter how to move. But the key word here, the one that causes all the trouble, is all. Every single kind of energy is supposed to be a source for gravity. No exceptions, no free passes.
And this is where we hit the catastrophe. Because our other great pillar of physics, quantum mechanics, has a totally different picture of empty space. It says the vacuum is not empty at all. No, it's this wild, seething, bubbling soup of virtual particles and energy constantly flickering in and out of existence. So, if Einstein's rule is right, if all energy creates gravity, then this enormous sea of vacuum energy should be creating the most powerful gravitational field you could possibly imagine.
So this is the question that's been keeping physicists up at night for decades. If the rule is that all energy has to gravitate, but we look out at the vacuum and see nothing, then just how wrong are our calculations? And the answer isn't just a little bit wrong. It's wrong on a scale that's hard to even describe.
This is the scale of the problem. Our theory's predicted value for the gravitational pull of the vacuum that is off by a factor of 1 followed by 120 zeros. To call this an error it doesn't do it justice. It's like aiming for the moon and missing the entire observable universe. It is the most spectacularly wrong prediction in the history of science.
Just let that sink in for a second. Not just in one field, but in the entire history of physics. If our standard theories were actually correct about this, the gravity from the vacuum would be so ridiculously strong that the entire universe would have crushed itself down into a space smaller than a pinhead moments after the Big Bang. The very fact that you and I are here to talk about this proves something is profoundly broken in our understanding. So, how do you even begin to fix something like that? For decades, the main idea was to invent some other mysterious energy that just perfectly canceled this one out. But what if we've been asking the wrong question the whole time? What if the problem isn't the amount of energy in the vacuum, but what gravity is actually capable of seeing and interacting with? Okay, this slide right here, this is the absolute core of the proposed solution. The standard view, on the left, is what got us into this mess. All energy creates gravity. But the BRSt model, on the right, suggests a radical shift in thinking. It says gravity is, it's picky. It doesn't just grab onto any old energy floating by. It only sees and couples to very specific, stable geometric structures. Now, I know geometric structures can sound a bit abstract and complicated, so to make this idea really click, let's use a super simple analogy to build a new picture of how gravity might actually be working. These special structures have a name, SPI hooks. You can think of them as these very specific, stable, geometric patterns that particles, like the protons and electrons that make you up, actually form. In this new model, these hooks are the only things in the whole universe that gravity has a handle to grab onto. So let's walk through this. Step 1, a particle of matter, like an electron, creates one of these stable geometric SB hooks. Think of it like a little coat hook. Gravity can come along and latch right onto it. Easy. Step 2, now think about the vacuum energy. It's different. It's more like random vibrations in the air, just background noise. It's full of energy, sure, but it hasn't organized itself into one of those nice, neat hooks. So step 3, gravity, which is only built to find and grab onto hooks, just sails right past all that background motion.
It's not that the energy isn't there, it's that gravity literally has no way to interact with it.
And that is the crucial punchline. This immense energy of the vacuum doesn't need to be canceled out by some cosmic coincidence. In this new view, gravity never even saw it in the first place. It is fundamentally, structurally, geometrically invisible to the gravitational force.
Now, that is a really elegant idea, right? But you might be thinking, does this concept of needing a specific structure for something to happen show up anywhere else in physics, or do we just invent it to solve this one problem? Well, it turns out this exact kind of logic is already a huge deal in another area of fundamental physics. Yeah, in a field called Yang-Mills theory, something called the mass gap problem shows the same principle. The idea is that for mass itself to even exist, energy has to organize itself into a specific, stable geometry. If it doesn't cross that structural threshold, you have energy, but you have no mass. This suggests that nature requires the right structure, not just the right amount of energy, for fundamental properties like mass, and maybe gravity too, to even show up.
This model even has an answer for those little quantum fluctuations, where virtual particles might pop into existence and briefly form a hook. Because these virtual hooks appear with totally random orientations and phases, some pointing up, some down, some left, some right, their effects are all over the place. When you average them out over any meaningful amount of time, their net gravitational pull is just zero. They cancel themselves out perfectly, which keeps the universe nice and stable.
Okay, let's bring this all home. Let's put the old catastrophic problem right next to this new structural solution and see just how neatly this whole mess seems to get resolved. This table just lays it out perfectly. The old physics started with the premise that all energy couples to gravity, which led to a head-on collision with what we actually see. The new solution just changes one core idea. Only SP hooks couple to gravity, and suddenly there's a clear mechanism. The vacuum has tons of motion, but zero stable hooks. The result isn't a conflict anymore, it's structurally inevitable. That bone in our throat is just gone, solved by making a simple distinction between raw energy and structured matter.
And this all leads to a really profound thought. For more than a century, we've told the story of physics is a story about energy. But this solution to its single biggest paradox hints at a totally different foundation. So I'll leave you with this question to ponder. What if the fundamental language of our universe isn't actually energy at all, but geometry? And what other huge problems might we solve if we start looking at reality through that lens?